few general things about radicals. For this chapter, a radical is an atom with one unpaired electron. These radicals are made through the homolytic cleavage of a covalent bond. They are reactive enough to interact with both sigma and pi bonds. They are more stable with more substitution, and these reactions have to take place in heat, light, or with a radical initiator, which includes peroxides with the general structure ROOR with a weak OO bond that's easily broken. Radicals can be classified as primary, secondary, or tertiary. You can find out its classification by looking at the number of R groups attached to the radical. There's 1 R group for primary, 2 for secondary, and 3 for tertiary. The reason why more substituted radicals are more stable is because they're favorable. This first one will form a primary radical, moving this electron to the hydrogen and this electron to the carbon will give you a product that looks like this. Moving these electrons around takes 110 kilojoules per mole. This one on the bottom will give you a secondary radical. Moving this one up to the H and the other electron down to the carbon down here will give you a radical that looks like this. Moving those electrons around only takes 397 kilojoules per mole because it's more favorable. If you're not sure at what kind of reaction you're looking at, look for what's required for it to proceed. If it needs heat, light, or peroxide, it's probably a radical reaction. If it has no rearrangements, it might also be a giveaway as to what kind of reaction it is. If the reaction slows or stops once oxygen, a radical scavenger, is added, it's probably a radical reaction. Now that we have an overview of what a radical reaction looks like, here's a very general mechanism. If the radical is interacting with a sigma bond, then the radical, which is very unhappy, will take 1 electron from this hydrogen over here. This makes an HX bond. This other leftover electron goes back to the carbon to make a carbon radical. If the radical is interacting with a pi bond, then 1 electron from the double bond and 1 electron from the radical come together to form a CX bond. The other electron that's left over goes to this carbon over here to give us a product that looks like this. If you want to stop a radical reaction, keep in mind that this is a chain reaction, so it's easily stopped if you break it. This can happen naturally when 2 radicals recombine to form a more stable one. You can also add in a radical inhibitor or scavenger like oxygen. These combine with the radical to give you a much more stable molecule. When you react an alkane with a halogen in the presence of heat or light, you get the corresponding alkyl halide. You can only use Cl2 and Br2 because F2 is too violent and I2 is too slow. In this example, methane is reacted with Cl2. One of the hydrogens will be replaced with a chlorine to give us a product that looks like this. When only one is replaced, this is called monohalogenation. You can get this product by lowering the concentration of Cl2. If the concentration of Cl2 is high enough, you can replace more hydrogens, giving you products like these. There are 3 steps in radical reactions. Initiation, which forms 2 new radicals that begin the cycle. Propagation, that forms new radicals from neutral compounds. And termination, which stops the reaction. Initiation forms 2 new radicals by homolytically cleaving the bond between these 2 halogens. This is going to give us a product that looks like this. Now we have two new radicals to start the propagation process. One of the chlorines that we just formed will come to interact with this neutral compound to make a new radical. Like before, one electron from this hydrogen and one electron from the radical come together to form a CH bond. The leftover electron goes back onto this carbon over here to give you products that look like this. This new carbon radical will interact with another Cl2 molecule. This electron from the carbon radical and one electron from this chlorine bond come together to form a CCl bond. This other leftover electron goes back onto this chlorine, which gives you products that look like this. This new chlorine radical can continue the cycle and react with this neutral molecule over here. There are three ways to stop this reaction. One of them is to add a radical scavenger like oxygen that will bind to these chlorine radicals and make them not as reactive. If there are no more neutral molecules to react with, these Cl radicals can combine back to form Cl2. These two ways stop the reaction up here. It cuts off the radical supply. Another way this reaction can be stopped is if two of these carbon radicals combine to form a much more stable product. This breaks the chain right here. What's the difference between using chlorine and bromine? Chlorination reactions aren't selective and proceed very quickly because they're exothermic. Bromination reactions, on the other hand, are very selective and go slower because they're endothermic. Let's take a look at this example. On this molecule, there are 6 primary hydrogens. There are also 2 secondary hydrogens. These are your 2 possible products. If we do this reaction with chlorine, which is pretty unselective, you might expect to get these products in a 3-to-1 ratio. This isn't what happens though. Even though chlorine is much less selective, it still prefers to add onto these secondary hydrogens. The actual ratio you'll get is a 1-to-1. If you do the same reaction with bromine, you'll get a near 0-to-1 ratio since it's so selective. The reason why chlorine is so much less selective is because it's exothermic. The CCl bond is much stronger than the CH bond. Bromine is more selective because it's endothermic. The CBr bond isn't as strong as the CH bond. Before we move on, let's look at some stereochemistry. Remember that achiral compounds are superimposable on their mirror images, while chiral compounds are not. In this example, we react butane, an achiral molecule, with Cl2. This will give us 2 constitutional isomers depending on which hydrogen is replaced. Replacing the primary hydrogen will give you a product that looks like this. If you replace on this second-degree hydrogen, you'll make a new stereocenter, which will give you 2 enantiomers. The reason why a racemic mixture forms when the reaction yields an sp2 radical is because of how the p orbitals are. The p orbital is perpendicular to the plane, with the electron moving in between these 2 lobes. This means that chlorine can attack from up here or down here. In this example, they are equally likely to add from both directions, so you will get an equal amount of each isomer. If your starting product is chiral, you have to look at where the reaction is taking place. If it's not happening on the stereocenter, then the configuration at that center is retained. If it is happening at the stereocenter, you have to look at the mechanism in order to know how the stereochemistry will behave. In this example, chlorination will take place at a chiral center. The radical intermediate looks like this. This is a planar radical, so the Cl can attack from either the top or the bottom. This will give you a pair of enantiomers. If the reaction doesn't happen at the stereocenter, make sure to check and see if a new one is formed. In this reaction, the chlorine radical reacts to form a new planar radical on this carbon. This gives us a new stereocenter. Chlorine can now attack from the front or the back. This is going to give us two stereocenters with different classifications. The original stereocenter, which is right here, keeps its R configuration no matter what product you look at. The second center's configuration depends on what side the chlorine attacked from. Front attack gives us an R configuration, while a backside attack gives us an S configuration. This is a pair of diastomers. A really good example of radical chemistry being used in real life is the ozone layer. When hit with sunlight, chemicals called CFCs turn into radicals. These radicals interact with the ozone, which is consumed as a reactant and forms O2. Because it's a radical reaction, just a little bit of CFC can destroy a lot of O3. New alternatives like HCFCs and HFCs decompose before they reach the ozone layer. Allylic carbons are the carbons adjacent to a double bond. These carbons can be turned into allylic radicals, which are even more stable than normal tertiary radicals. NBS contains a weak NBr bond that can selectively halogenate allylic compounds. The reason why allylic radicals are so much more stable than other radicals is because of resonance. This electron can also move over here, which will give us a hybrid structure that looks like this. The electron is delocalized and has more freedom, making it much more stable. Allylic bromination with NBS has the same steps as any other radical reaction. This weak NBr bond is going to be homolytically cleaved to give you a bromine radical. This bromine radical can now interact with an allylic compound to make an allylic radical. This allylic radical can now interact with the Br2 formed by the NBS. One electron from the carbon radical and one electron from this Br bond come together to form a CBr bond, and this other electron that's left over goes to the other Br to give you this product. Steps 2 to 3 can repeat over and over until the cycle is broken. Here are some quick real-life examples Dr. Muru talked about in class, just in case they're on the test. Oil has a shelf life because it can react with oxygen that's in the air. This will turn its allylic carbons into peroxides. Antioxidants like vitamin E and BHT use a phenol that has an easily lost H that radicals take to stabilize themselves. In the presence of heat or light, HBr will add to alkenes to form alkyl bromides. With unsymmetrical alkenes, radical addition will add Br to the less substituted carbon, while ionic addition will add the H onto the least substituted carbon. Only HBr will do these addition reactions. HCl and HI both aren't favorable for this type of reaction. Initiation with ROOR happens in 2 steps. Homolysis of the weak OO bond, and the extraction of H to form this bromine radical. This bromine gets added to the terminal carbon, which makes an allylic radical. Abstraction of H from HBr forms a new CH bond and a new bromine radical. This new bromine radical can enter back into the cycle, letting steps 3 and 4 repeat until termination. Just in case it's on the test, polymers are made of monomers. They can be made with radical reactions called head-to-tail polymerization. If you took cell bio or any other chemistry course, you already know that different substituents give it different properties. Congratulations, you made it to the end of chapter 13.